So good morning to all. Today we will again start with the third class of electrical machine. So far we have discussed about the basics of electrical machine, that is the transformer. I have given you the definition of the transformer. I have given you the principle on which the transformer is based. I have taught you some terms related to the constructional features of transformer, that is what is a primary winding, what is a secondary winding, what is a core, of what material core is made up of what material the winding is made up of. I think so there is no doubt so far, because no one has asked any doubt, so I will assume that you have fully understood the things which I have told. Today we are going to start with another topic related to transformer, that is the so my screen is visible to you or not? Please tell me.
They're visible.
Okay, fine. So today what we are going to study, that how an ideal transformer operates. Somewhat I have already told you in my previous slides. What is the voltage and current relationship between the two windings in an ideal transformer? So we will also learn what is an ideal transformer is, then what is the voltage and current relationship inside it. Then we will also learn about the reflected impedance through a transformer. Then we will also go through the no load currents that flowed in a non-ideal transformer, and then we will draw the no load circuit model of a non-ideal transformer. So basically, in short, we can say we will study what is the ideal transformer and what is a non-ideal transformer. Okay, so these are the learning objectives of this class. Okay, so let us start. Now, principle I have already explained you, that how an ideal transformer works. First of all, what ideal transformer is? In an ideal transformer, there is a no losses is there. There are two types of losses are there, iron loss and copper loss. But this type of losses are absent in ideal transformer. So whatever the input, this is your input side, whatever the input you will provide here, you will get the output here. That is, input power is equal to output power in case of an ideal transformer. Okay, so I can say P input is equal to P out. Okay, a P input is equal to P out. What does this mean? It means there is no losses in the system. Losses are of two types. One is known as iron loss and another is known as the copper loss. So we will assume that these losses are absent in ideal transformer. Second thing, so first condition is clear in ideal transformer. So you can be asked, define ideal transformer. So what you will say? Ideal transformer means where there is a no losses there, no iron loss, no copper loss. Whatever input power is being fed on the primary side, the same output power we will get on the output side. Voltage or current on the either side will change, but power input is equal to power output. Another is that there is no leakage flux is there. Leakage of flux is absent. Now what does this mean by leakage of flux? Now what happens? I have already explained you that when a source, an AC source is being connected to the winding on the primary side, okay, what will happen? Current flows through the windings. Current will flow in this winding. These are the turns. These are called the turns. What they are called? They are called turns. So we have turns on primary winding. We have turns on the secondary winding. Okay. Now the winding on which load is connected is called is called secondary winding, while the winding on which the source is being connected is called primary winding, and the winding on which load is connected is called secondary winding. I think so it is clear. Any doubt so far you can ask me immediately.
सर पीपीटी विजिबल नहीं है.
विजिबल है सर.
Maybe it may be your problem in your internet. Your internet connectivity may be poor, but somebody are saying please respond me in the chat box. Is PPT is visible?
Yes sir. Yes sir.
Okay. So you are you seeing my annotations also? I am writing P input is equal to P output. Leakage flux is absent. That is also visible.
Yes sir.
Okay, fine. So probably those who are not able to see it, maybe their connectivity problem will be there, but you will get everything on the YouTube also. So after the class is over, you can see the YouTube video also. So primary and secondary winding concept is clear. I was giving the concept regarding the ideal transformer. So in an ideal transformer, what happens? P input is equal to P output. Leakage flux is absent. What do you mean by leakage flux? Now what happens? When you apply primary source current to the primary winding, what happens? Current will produce, and due to which flux is produced. You can see these dotted line are flux. Now whatever flux is being produced by the primary winding, okay, the whole flux is linked to the secondary winding. There is no such flux. For example, there is a flux like this. Now what happens? This flux is linking primary only. This flux is not linking the secondary winding. So this flux which is being produced by primary winding linking only the primary winding is called a leakage flux. Okay. While the flux which is common to both is not leakage flux. Okay. The flux which is similarly on the secondary winding, if some flux is produced which is linking only secondary winding, that is called leakage flux. Later on we will introduce a leakage reactance also, or leakage impedance also corresponding to the leakage flux. But at present in ideal transformer, we assume that there is no such leakage flux is there. Whatever flux is being produced by primary winding, the whole flux is linked to the secondary winding, and whatever secondary winding is producing is linked to the primary winding. This is what by the leakage flux is absent. I think so it is very clear that input power is equal to output power, no losses is there, and leakage flux is absent in case of an ideal transformer. So what happens in an ideal transformer? Let us see. I have applied an primary voltage, an AC voltage source. You can see the symbol of the AC. Okay. I have applied an AC source, like you can see this is the symbol of the sinusoidal voltage source is being applied to the primary winding. So when current flows through primary winding, a magnetic flux is produced. Okay. You can see how flux is being produced. Animation is also being shown to you that how flux is being produced. Okay. So whatever flux being produced by the primary winding is linking not only primary, it is also linking the secondary winding. So what is happening basically? What happens that the flux is linking primary also, secondary also. So an induced EMF is produced into the primary winding also. Let it be EP1, EP dash. Same flux is linking the secondary winding also. Let the induced EMF produces ES dash as shown in the figure. I think so the terms are clear. So we have an induced EMF on the primary winding which is being designated as EP dash, and we have a induced EMF on the secondary winding ES dash. Now what is the magnitude of this EMF? Okay, this magnitude is being governed, and the direction, both magnitude and direction are both governed by the combined Faraday's second law and Lenge's law, which state that the Faraday's second law state that induced EMF is directly proportional to the rate of change of magnetic flux, and Lenge's law state that the magnetic flux flow in the induced EMF so produce flow in such a direction that it opposes the very cause. Okay, so you can see in mathematically form I can write the induced EMF on the primary siding, let it be even. Please wait. The induced EMF on the primary side is minus is because it always opposes the cause. N1 is the number of the turns on the primary winding. What is N1? N1 is the number of the turns on the primary winding. Okay, number of turns on primary winding. While N2, similarly induced EMF is produced on the secondary winding also. That is again equal to minus because of Lenz's law. That is number of turns on the secondary windings and the rate of change of flux. And this flux maximum
सर
value.
पीपीटी विजिबल नहीं है। यूट्यूब पे भी नहीं है सर। सर लिख रहे हो वो दिख रहा है बस।
है
लिख रहे हो वो आ रहा है सर, बाकी पीपीटी नहीं दिख रही है सर।
What about the other people?
नहीं आ रही है, इससे तो
सर
नहीं आ
किसी को
रही
नहीं दिख रही है।
पीपीटी नहीं खोल रखी सर आपने वो।
खाली पीपीटी ली तो वो सर फाइल दिख रही है, तो ये फाइल पड़ी है यहाँ पे।
अच्छा, जो अंदर का वो नहीं दिख रहा है।
सर कब से नहीं दिख रहा
सर
है।
खाली अब लिख रहा हूँ ना, ये ट्रांसफार्मर है, ये वो है, तो वही दिख रहा है खाली।
अच्छा, जो अंदर जो डायग्राम बना हुआ वो नहीं दिख रहा है।
यस
नो
सर नहीं
सर।
दिख रहा है सर।
ओके, आई विल चेक इट।
सर यूट्यूब पर भी विजिबल नहीं है।
ओके, लेट अस चेक।
सर अब विजिबल है। It is visible now?
Yes, sir.
Yes, sir.
It is visible now?
Yes.
Are you seeing the diagram of the transformer?
Yes, sir.
Yes, sir.
So, what I was explaining? I was explaining about the transformer working of an ideal transformer. Okay, so I have already told you that an ideal transformer means that the input power is equal to output power, and also I was telling that there is no leakage flux is there. Okay, and the flux concept I have already given you. Okay. Okay, so what I have told you that when PPD is visible.
Yes, sir. Now visible.
So there is a alternating voltage source is there, AC source is there. It is being applied to this winding. So this winding is your primary winding, and load is being connected to this winding, which is called secondary winding. Okay, so whenever current will flow through this winding, what happens? An induced EMF is a flux will be produced. Now this flux in ideal transformer, whatever flux is being produced by the primary winding, it will be linking the whole secondary winding like this case. Okay, you can see it. Okay, so whatever there is, now there will be some flux like this. In non-ideal transformer, there will be some flux while like this. Now this type of flux which is linking only the primary winding but not linking the secondary winding is called leakage flux. But in case of ideal transformer, we will assume that there is this leakage flux is absent and only the main flux is there, which is linking primary as well as secondary winding, and the maximum value of this flux is phi m. So according to the Faraday's second law and according to the Lange's law, what happens? An induced EMF is produced in both primary as well as in secondary, because this varying flux which is produced due to flow of AC current is linking both the winding, primary and secondary. Primary और secondary दोनों को link कर रहा है, इसलिए ये दोनों में इंड्यूस ईएमएफ प्रोड्यूस करेगा। और प्राइमरी का हमने डिनोट किया ईपी डैश से और सेकेंडरी का हमने डिनोट किया ईएस डैश से। इज इट क्लियर? सो इंड्यूस ईएमएफ इज प्रोड्यूस इन बोथ द वाइंडिंग, एंड व्हाट इज द मैग्नीट्यूड एंड डायरेक्शन ऑफ दिस इंड्यूस ईएमएफ? दैट इज बीइंग गिवन बाय Faraday's second law. Okay, so you can see through an animation that how flux is being produced and how this flux is linking the primary as well as secondary winding, and due to which an induced EMF is produced. Okay, so you can see the magnitude value. Are you seeing the magnitude value? According to the Faraday's second law and Lange's law, that is induced EMF, it should be EP dash is equal to minus N1. What is N1? What is N1 here?
Number of primary terms.
Yes, number of turns on the primary side, and N2 is this N2 which you are seeing is the number of the turns on the secondary side, like this. On this is this. Okay, so according to Faraday's second law, it is directly proportional rate of flux linkage. Now flux linkage is nothing but N into phi m. N being constant, it has been taken out, minus m d phi m by dt. Maximum value we are taking here. Similarly here N2 d phi m by d2. So these are the two induced EMF produced on the either side, that is on the primary and the secondary winding. Okay, so now we will find out the okay, so you can see for sinusoidal sources. Now for sinusoidal sources, okay, this primary voltage, by putting the value of in the so-called the formula which is given by Faraday's second law and by Lange's law, we find that the primary voltage induced EMF comes out to be 4.44 NPF phi max. Okay, it is very simple. You need not have to worry about it. Just you place the value of this. Okay, you will get this value 4.44 NPF phi maximum. Similarly, the secondary voltage induced EMF secondary voltage ES dash is also come out to 4.44 NSF phi max, where NP is the number of turns on the primary side and NS is the number of turns on the secondary side. So if you divide the equation 1 by equation 2, what you will get that the second primary induced voltage, the ratio of primary induced voltage to secondary induced voltage is nothing but NP by NS. Okay, so this is the voltage relationship for an ideal transformer. That is, the induced EMF so produced is directly proportional to their turn ratio. That is, EP dash upon ES dash is nothing but NP upon NS, where NP is the turns, number of turns in the primary coil or primary winding, and NS is the number of turns in the secondary coil or secondary winding. Okay, so this is also called the voltage ratio. This ratio is also called voltage ratio. If you talk in terms of voltage, that is called voltage ratio, and if you talk in terms of turn ratio, turns, that is called turn ratio. Is there any doubt so far in this?
No, sir.
Okay, so don't get confused. Whenever you are being told turn ratio, then you will always say it is NP over NS. So again, I am telling you what an ideal transformer is. Okay, somewhat I have background I have given you, that the input power is equal to output power. That has been elaborated in the third point. No power losses. No power losses is there. Now losses are of two types in transformer: the iron loss and the copper loss. Okay, iron loss is due to the core, and copper loss is due to the winding. So all the second and third both are indicating the same, that there is no iron loss and no copper loss. Okay, in other words, in ideal transformer losses are absent. जो हमने इनपुट पावर दिया है वह का हमें आउटपुट पावर मिलेगा, केवल फेरबदल किसमें रहेगा? वोल्टेज और करंट में. एक तरफ वोल्टेज बढ़ जाएगा तो करंट घट जाएगा, एक तरफ वोल्टेज घट जाएगा तो करंट बढ़ जाएगा, लेकिन पावर दोनों के साइड सेम ही रहेगी. सो दैट इज व्हाई, can anybody can tell me in which unit we used to express the transformer power rating? The power rating of a transformer, जैसे हम मोटर खरीदने जाते हैं, 5 हॉर्स पावर की दे दो या 3 हॉर्स पावर की दे दो, KVA. Yes, the transformer rating is always expressed in KVA. Why it is expressed? This is also a very good question that we will tell you later on. But you should always remember that transformer rating is mentioned in a smaller, for a smaller laboratory transformer it is volt ampere, okay, VA, and for a bigger transformer it is KVA, and for bigger power transfer it is MVA, mega volt ampere, kilovolt ampere, and simply volt ampere. So this type of you find in the laboratories, this you will find in your nearby distribution transformer, okay, and this you will find in the transmission and generating substation MVA rating. So transformer power rating is in volt ampere, and the higher units are also being shown to you. I think so it is clear. So here we will assume that losses are absent. So second and third point is clear. Third, all flux produced in the primary coil links to the secondary coil. The same concept I have given you. The first and the fourth point. Okay, the first point, that is whatever flux is being produced by the primary, the whole is being linked to the secondary. There is no leakage is there. So no leakage flux, no leakage impedance, no leakage reactance. That is absent in case of an ideal transformer. Permeability is infinite. What does this mean? That there is no saturation is there. What happens? That this core of the transformer, which is generally made up of silicon steel, or in some low power device it is made up of iron. There is a one property that up to a particular limit they behave as a linear. So if you will draw the characteristics of an core, the BH curve, then you will find that they are generally having this type of characteristics. But after a certain limit, the whatever current you flows, there no magnetic field will be developed, that it gets saturated. So this constant region is called saturation region. So we will also assume that there is no saturation is there, it will always behave in this linear region. So this is also one of the important point. No power loss has already been accommodated in this point, that is winding have zero resistance. Okay, that we have already covered in the point number 3. Moreover, no current required to magnetize the iron core. Okay, that is also, that is there is no magnetizing current is being drawn, simply the magnet is already having the magnetic field. So these are the certain conditions, okay, which we assume for an ideal transformer. Okay, now no doubt they have a physical justification also. Okay, the resistance, zero resistance, when I say zero low resistance, it is very low resistance. Okay, for example 0.01 ohm resistance, then we will assume that this resistance is negligible. Similarly, no doubt current is required to magnetize the iron core, but that current is suppose say 0.1%, then again we can neglect it and we can assume it that it is nearby to the ideal transformer. Though this type of situation is not present in the power or distribution transformer, in laboratory transformer you can have a near about ideal transformer, but ideally means which has the efficiency of greater than 99%. Okay, truly speaking it should have 100%, but we can neglect the losses, then we can make it in an ideal transformer. And for an ideal transformer, the turn ratio is nothing but EP dash upon ES dash, which we have already derived it, or number of primary windings upon number of secondary windings. And since in an ideal transformer EP dash is equal to VP, VP is what? Applied voltage. And what is VS? VS is the voltage of the across the load. Now see, look towards the figure. I will again move to that figure so that things will get clear. See, this was VP. Mind it, student get confused. This is VP, where which is a VT. Basically, this is VP, and the voltage across. Sorry, this is your VP, and this is your VS. This is your EP dash, and this is your ES dash. This is the applied voltage. This is the terminal voltage across the load. This is the induced EMF across the secondary winding, and this is the induced EMF across the primary winding. I think so. Now there is no doubt, there is no confusion that what is EP and what is VP. VP and EP are two different things, but in an ideal transformer, both are equal. Similarly, VS and ES dash are both different terms, but in an ideal transformer they are equal. So we can also say that the primary winding is equal to, the turn ratio is also equal to the rated primary voltage upon the rated secondary voltage. So this VP and VS are called the rated primary voltage and rated secondary voltage. Is it clear or not, or is there any doubt? Then you can speak out. Is there any doubt?
No, sir.
Okay, fine. So let us move to the some. Now we talked in terms of mathematics that this turn ratio, in some books it is written by n, some it is written by a. So this is a scalar quantity. Be clear in this respect, and it introduces no phase shift. So turn ratio is simply a scalar quantity, and its importance is that it changes the voltage or current level, but it does not change in the phase shift. Similarly, we can have a power balance also. The power balance, that is on the primary side, EP into IP, and ES is equal to ES into IS, because there are no losses is there in the transformer. Therefore the apparent power on both the side will be equal, that is SP is equal to SS, that is primary apparent power is equal to secondary apparent power. Now as far as current ratio is concerned, that is the ratio of IP over IS, then with the help of this equation, this power balance equation, okay, you can find out that this ratio of primary current to that of the secondary current is the inverse of the turn ratio, that is 1 upon A. Okay, so don't get confused, and I think so this you have learned in the lower classes also, but how it has been derived you can see in this point. So current ratio is the inverse of the voltage ratio. Okay, now we will talk about another concept called the reflection of the impedances. Okay, now what happens? You know that if this is a transformer is there, if I'm looking toward this side, then what will be my input impedance? It will be EP upon IP. In fact, it should be EP dash. So I am not writing EP dash. There is some problem is there. Okay, but it is EP dash upon IP. This is the impedance as looked from the primary side. Okay, Similarly, we have a load impedance Z load, and that will be equal to ES upon IS or ES dash upon IS. Now, if I will express ES and IS in terms of primary values by taking the turn ratio, then what I will get, ES is equal to EP upon A. That is very clear. And similarly, secondary current IS is equal to turn ratio multiplied by primary current. Okay, I think so. It is clear, very much clear by the equation what we have developed so far. जो हमने अभी इक्वेशन डेवलप की है उससे ये क्लियर हो गया है कि जो सेकेंडरी वोल्टेज है ES वो कितना है, EP अपॉन A, और प्राइमरी सेकेंडरी करंट है वो है टर्न रेशियो मल्टीप्लाई बाय प्राइमरी करंट. So what we get, if I take ES over IS ratio, then I will get EP upon A multiplied by IP like this. See this, looks toward this. ES upon IS. ES I have taken from this side. IS I have taken from this side. आप देख लीजिए, इनको प्लेस कीजिए, आपको क्या अल्टीमेटली क्या मिलेगा कि ES over IS ratio, that is nothing but EP upon IP 1 upon A square, that is 1 upon the turn ratio square, 1 upon the turn ratio square. What is ES over IS? And what is EP over IS? This is nothing but Z input. And what is ES over IS? This is Z load. So what conclusion is that Z load in terms of primary impedance, it can be expressed as Z input upon A square, that is turn ratio square. Okay, so that conclusion we have got. Okay, Z load is equal to Z input upon 1 upon A square, or Z load into A square is equal to Z input. This is a very important ratio, that how you can express the output load impedance in terms of the input primary impedance. Input primary impedance, that is the load impedance, is nothing but is 1 upon A square times the Z input. Clear? So this is a very important derivation for an ideal transformer. Mind it. Now there is another question, is that derive equation when impedances are connected to the primary side and viewed from the secondary side. Mind it, that suppose we want to view it from the secondary side. The previously we have viewed from the primary side. Now we are viewing from the primary side. So in this case, Z input will be nothing but ES over IS. Okay, and your Z load will be EP upon IP. So when you will substitute the same thing here, what you will get, now Z load as viewed from the primary side, as viewed from the secondary side, will be nothing but what? Will be nothing but, yes, look towards the board, what Z load, okay, as viewed from the secondary side will be nothing but Z input multiplied by turn ratio square. So this is just an inverse of what we have viewed from the primary side. In the primary side, Z load was Z input upon A square, but when viewed from the secondary side, Z load is equal to turn ratio square multiplied by Z input. This you have to keep in the mind, okay, because this will be useful in the transformer equivalent impedance of a non-ideal transformer. Is it clear? The same concept will be utilized in the equivalent circuit of a non-ideal transformer. Okay, so there you have to keep in the mind from which side you are viewing. If you are viewing from the primary side, then the Z load will be equal to the Z input upon A square, and if you are viewing from the secondary side, for example this side, then Z load will be equal to Z input multiplied by A square. This is to be kept into mind. Now let us take a numerical. Now before doing the numerical, you should understand each and every language of an numericals. What is written here? Read it silently. I am reading for you. 25 kVA. So what does this mean? What this value indicate? This indicate that a transformer is there whose power rating is what? 25 kilovolt ampere. K means kilovolt ampere is the basic unit of the transformer. So it is having kVA. It is not kilowatt. This what I want to stress. This is not kilowatt. This is your kilovolt. How much? 25 kilovolt, comma 7200 minus 240 oblique 122 center tape. Now what does this mean? So the first value will always be a primary value, primary voltage. Mind it. This you have to keep in mind, that for the first voltage will be always what? Your primary applied voltage Vp. This you have to keep in mind. Okay. And the second voltage will be always be a secondary voltage 240. But here it is also being written one more thing. This type of numerical you will not find in many books. But this I am intentionally taking this numerical for you so that you can understand this type of numerical. In generally books you will have 25 kVA, comma 7200 oblique 240, like this. Here 240 oblique 120 is written. That is intentionally being written. I will tell you later now. But generally you will find. So this first voltage will be always your primary voltage, and this will be always your secondary voltage. This you have to keep in the mind. Clear? So here it is 240 by 120. It means the total voltage across the secondary winding is 240, but it is being center tape. Center मतलब बीच में, इसको center tape कर दिया गया है. जैसे देखिए ये ट्रांसफॉर्मर बना, आपका प्राइमरी साइड कितना है 7200 वोल्ट, और सेकेंडरी साइड आपके टोटल तो कितना है 240 वोल्ट, लेकिन बीच में से अगर आप एक और वायर लेंगे तो ऊपर कितना मिलेगा 120 वोल्ट, और नीचे साइड में कितना मिलेगा 120 वोल्ट, जो जिनको जब ऐड करेंगे तो वो कितना हो जाएगा 240 वोल्ट. दैट इज व्हाट मीन बाय सेंटर टेप. This type of problem you will not find in many books, but especially I have taken for you intentionally so that center tape concept is also clear. Now again, what is written? Single phase. कुछ लोग कुछ बुक्स में आपको सिंबल के साथ मिलेगा, इस प्रकार लिखा हुआ. In some books you will find in this way, single phase, it is like this. Had it been three phase, in the next topic we will have a three-phase transformer. It is right later. So you have to be very careful, see it, what is its power rating, what is its primary voltage, what is its secondary voltage, whether it is a single phase or a three-phase. So every word you have to read. Okay. Operates as a rated voltage. Operates as rated voltage means on the primary also the rated voltage is 7200, and on the secondary also 240 volt is being applied. 240 volt we are getting. So it supplies a single phase load that has an equivalent impedance of 7.2 angle 36.9 ohms. Assume ideal operation and find turn ratio. ठीक है, अब यहाँ पर इन्होंने एक प्राइमरी वोल्टेज 7200 वोल्ट लगा दिया, और यहाँ पे इन्होंने एक लोड लगा दिया जिसकी वैल्यू कितनी है 7.2 और एंगल 36.9 डिग्री ओम्स है. इज इट क्लियर? तो अब ये एक एक क्वेश्चन आपसे पूछा है, टर्न रेशियो फाइंड आउट करें. तो टर्न रेशियो बहुत इजी है. क्या होता है हमारा ईपी ओवर EAS. EP कितना है 7200 वोल्ट, ठीक है, और ES कितना है, ठीक है, कितना है 240 वोल्ट, ओवरऑल 240 वोल्ट है, तो 7200 डिवाइडेड बाय 240 विल गिव यू 30. सो 30 इज द फर्स्ट आंसर. क्लियर? 30 इज द फर्स्ट आंसर. इसमें कोई डाउट है? कोई प्रॉब्लम नहीं. सेंटर टेप का कंफ्यूज मत करना, क्योंकि ओवरऑल टर्न रेशियो हम टोटल वोल्टेज कितना आ रहा उससे लेंगे, 120 से नहीं लेकर 240 से लेंगे. सो डोंट गेट कंफ्यूज. दूसरा क्वेश्चन क्या है? सेकेंडरी करंट. ओके, लेट अस फाइंड आउट सेकेंडरी करंट. So for secondary current, okay, we first of find out the secondary current will be how much. So for that purpose we have to find out the how much voltage is there on the secondary side. This is 240 angle 0 degree, okay, and the impedance value is already be given in the question, 7.2 angle 36.9 degree. Okay, so secondary current comes out to be this much, 33.33. 240 divided by 7.2 volt will give you 33.33 value, and your 0 minus 36, that is minus 36.9 degree. Is there any problem so far? No. So what is the next question? Let us take two points we have already covered. Primary current. Now to find out the primary current we will use again the turn ratio concept. Okay, we know that primary ratio of primary current over secondary current is nothing but inverse of the turn ratio 1 upon A. Therefore primary current will be nothing but secondary current divided by turn ratio. Secondary current divided by turn ratio. So find the primary current. It is 1 upon A. So 1 upon A is nothing but 1 upon 30, which you have already calculated, and therefore you will get primary current is 1.11 minus 36.9 degree ampere. Clear? Now that question, find the input impedance as seen from the primary side. I have already told you that as viewed from the primary side, Z load is equal to Z input upon A square. Z load is equal to Z load is equal to Z input upon A square. So Z input will be equal to A square into Z load. Z load is already being given 7.2 3.69. This is already good. A square we have already calculated. So Z input as viewed from the primary side will comes out to be 6480 angle 36.9 degree ohm for an ideal transformer. I think so. This is clear. Now if you are asked find out the power and the power factor of the load. So what we'll do, you know that the apparent power is nothing but the total power, that is also known as the total power, is either the V multiplied by complex conjugate of the current or complex conjugate of the current multiplied by V. Is it clear? Both can be used. So here the complex conjugate of the secondary current multiplied by the secondary voltage has been used. So when I will place what I will get, the secondary is nothing but 240 angle 0 degree, and IS I have already find out minus 30. I will take its complex conjugate. Just in complex conjugate the angle changes, magnitude does not changes. So minus will become plus. So when I will multiply the two polar quantities, I will get 8000 angle 36.9 volt ampere. It will be volt ampere. You can also express in kilovolt by dividing by 1000. So it will be 8 angle 36.9 degree kVA. Similarly, on the primary side, you can calculate the apparent power. It will be complex conjugate of the primary current multiplied by the primary voltage, which we have already calculated it. You can see, just multiply it with 8000 angle 36.9 degree volt ampere or 8 kVA, 8 angle 36.9 degree kVA. You can also write in kVA form also. Okay, I can also write 8 angle 36.9 degree kVA. Okay, and similarly on this also side. So what you find in the ideal transformer, both input power is equal to output power, and there is no phase shift is there. There is no phase shift. Whatever the angle 36.9 degree on this side, about 36.9 degree on this side. Now power factor. How to find out the power factor? Okay. Power factor is very easy. Power factor is nothing but the phase difference between the voltage and current. On both the side, primary and secondary side, we have assumed the angle to be 0 degree. So the current is finite having an angle of 36.9 degree. Okay, you can see it. I will just move it, that what you will find out in your previous questions. For example, what you find? Minus 36.9 degree. What about the secondary? The secondary is the primary, secondary is also minus 36.9. So minus 36.9 is current is lagging the voltage by an angle of 36.9 degree. So current is lagging. So you can find out the cos of 36.9 degree. So when you find out the cos of 36.9 degree, you can find out the power factor. Okay. And similarly, you can find out the power and the corresponding the active power and the reactive power. So if I take 8000 cos 36.9, it is comes out to be 6090 is the active power. Okay, and the reactive power is nothing but 8400 is, and I can also find out cos 36.9 degree, that is come out 0.80, or I can divide this active power upon upon the total power, that is come out to be 0.80. So both methods can be used. Either you take cos of 36.9 degree, that is also equal to power factor, or I can take the active power, this is the active power, divided by the apparent power, that is 8000, I will get 0.80, and since the current is lagging, so this power factor is called 0.80 lagging. ये power factor चूंकि current lag कर रहा है, वोल्टेज का एंगल कितना है 0 डिग्री और करंट का एंगल कितना आ रहा है माइनस 36.9, तो करंट लैग कर रहा है, और हम पावर फैक्टर को वैसे डिफाइन करते हैं कि करंट कैसे लैग कर रहा है, लीड कर रहा है, या लैग कर रहा है, तो हम पावर फैक्टर को कहेंगे 0.80 लैगिंग. इसमें कोई डाउट? इसमें कोई डाउट? इसमें कोई डाउट? लैग और लीड वाला देखिए, जो लैग और लीड कॉन्सेप्ट है जो हम यूज करते हैं ऑर्डिनरी टेक्स्ट बुक्स, सभी टेक्स्ट बुक्स में, स्टैंडर्ड टेक्स्ट बुक्स में भी, वो हम करते हैं वोल्टेज को रेफरेंस मानते हैं और उसके रेस्पेक्ट में करंट उससे ऊपर है या नीचे है। फेजर डायग्राम से हम ज्यादा अच्छी तरह से समझ सकते हैं। जैसे ये मैंने रेफरेंस ले लिया वोल्टेज, ठीक है। अगर मेरा करंट ऐसे है तो करंट एंटी क्लॉकवाइज में आगे बढ़ रहा है, इसका मतलब करंट आगे है किसके? वोल्टेज के। मान लो ये डिग्री है 30 डिग्री, और cos 30 डिग्री कितना होता है? cos 30 डिग्री कितना होता है? hmm? 0.866 something. Okay, now since current is leading by voltage, so I will call this power factor as a leading power factor, क्योंकि करंट लीड कर रहा है। अब मेरा एक दूसरा केस लीजिए, ये मेरा वोल्टेज है 0 डिग्री पे और करंट मेरा यहां पे नीचे की साइड, क्लॉकवाइज डायरेक्शन में नीचे की साइड चला, इधर की साइड चला गया, तो करंट लैग कर रहा है किससे? वोल्टेज के। अगर वो एंटी क्लॉकवाइज में आगे है तो लीड है, अगर वो क्लॉकवाइज में नीचे आ रहा है तो वो क्या है? लैग में। अब cos अगेन 30 डिग्री कितना? 0.866, तो मैं इस पावर फैक्टर, इसके पावर फैक्टर को क्या कहूंगा? 0.866 लैग। क्लियर? ये समझ में आया कि नहीं आया कि किसको मैं लैग कहूंगा और किसको मैं लीड कहूंगा? लीड हम हमेशा वोल्टेज को रेफरेंस लेते हैं। अब मान लो एक और प्रॉब्लम है कि वोल्टेज है 50 डिग्री, वोल्टेज का एंगल है 50 डिग्री और करंट का एंगल है 30 डिग्री। अब बताइए करंट लैग कर रहा है या लीड कर रहा है? पहले बताओ। तो ये 50 डिग्री मेरा रेफरेंस हो गया, ये 30 डिग्री, तो ये इस प्रकार देखिए, अगर डायग्राम बनाऊंगा, ये मेरा वोल्टेज 50 डिग्री पे है और ये मेरा करंट 30 डिग्री पे, तो ये हो गया मेरा करंट अब ये 50 डिग्री और ये मेरा 30 डिग्री। तो अगेन अगर इसको रेफरेंस मान लूं तो इसके पीछे कितना एंगल है? 20 डिग्री। डिफरेंस कितना है? 20 डिग्री। तो मुझे cos 20 डिग्री निकालना पड़ेगा। cos 20 डिग्री जितना भी आएगा उसके आगे मैं लगा दूंगा लैग, क्योंकि करंट इज लैगिंग द वोल्टेज। इस यही उल्टा होता, करंट होता 50 डिग्री, करंट होता 50 डिग्री और वोल्टेज होगा मान लो आपके 30 डिग्री। तो ये मेरा रेफरेंस 0 डिग्री, वोल्टेज मेरा हो गया कितना? 30 डिग्री और करंट हो गया मेरा, करंट हो गया मेरा 50 डिग्री ऐसे। तो अब क्या हो रहा है? करंट इज लीडिंग, करंट इज लीडिंग, ये करंट 50 डिग्री वाला है और ये 30, करंट इज लीडिंग बाय 20 डिग्री, सो आई विल फाइंड cos 20 डिग्री and whatever the value it comes out to be, I will say leading power factor. Is there any doubt so far? ये पावर फैक्टर का कंसेप्ट में कोई डाउट है? Okay. So now we take another numerical. Again it is related to the ideal transformer. Okay, a 300 kVA 2400, either somebody use like this or in books you will find like this. I will just show you, or in like this also slash. So this is your primary voltage and this is your secondary. 60 hertz. In India it is 50 hertz. In America and some other countries it is 60 hertz. Single phase transformer operated at 2003. Now it is not operating at rated voltage, mind it, on the primary side. If I say that operates at the rated voltage, means it would have operated at 2400 voltage. मगर यह क्या कह रहा है? इसकी रेटिंग तो इतनी है, मैक्सिमम रेटिंग कितनी है प्राइमरी साइड? 2400, लेकिन फिर भी हमने वोल्टेज कितना दिया इसको? 2300 वोल्ट ऑन द प्राइमरी साइड। फिर क्या कह रहा है? इट सप्लाइज 115 kVA to a load that is a power factor of 0.72 lagging. Assume ideal operation and find secondary voltage, operating voltage, secondary current, impedance of the load as seen on the secondary impedance of the load. ये चार हमें निकालने हैं। ये थोड़ा सा अलग है, अलग इन द सेंस ये है कि अब ये फुल लोड पे ऑपरेट नहीं कर रहा है, प्राइमरी साइड पे कितना कर रहा है, कुछ बिलो कर रहा है। कितना है फुल लोड, कितना 2400 और ऑपरेट कितने पे कर रहा है 2300। तो इस टाइप के प्रॉब्लम को कैसे हैंडल किया जाए, लेट अस सी। फाइंड आउट फर्स्ट ऑफ ऑल सेकेंडरी वोल्टेज एट ऑपरेटिंग वोल्टेज। इज इट क्लियर? अगर प्राइमरी 2400 पे ऑपरेट करता तो सेकेंडरी कितने पे करता? क्वेश्चन को देखिए वापस। अगर प्राइमरी 2400 पे करता तो एक आइडियल ट्रांसफार्मर में सेकेंडरी कितने वोल्टेज पे करता? टेल मी फास्ट। नो वन इज टेलिंग। अगर प्राइमरी 2400 वोल्टेज पे ऑपरेट करता तो सेकेंडरी में वोल्टेज कितना मिलता हमें? हाउ मच वोल्टेज वी वुड हैव गॉट ऑन द सेकेंडरी साइड? 120। लेकिन ये तो हमारा 80 क्यों? तो पहले हम टर्न रेशियो निकालते हैं। टर्न रेशियो कितना होगा, जिसको हम ए कहते हैं, सॉरी टर्न रेशियो को हम ए कहते हैं, वो कितना होगा 2400 डिवाइडेड बाय 120। ये 0 कैंसिल हो गया, ये कितना हो गया आपके 240, कितना हो गया आपके 12 20। सो टर्न रेशियो कम्स आउट टू बी हाउ मच 20। ठीक है, अब हम लेकिन प्राइमरी कितने पे ऑपरेट कर रहा है 2300 वोल्टेज पे। 80 गलत आंसर है जो भी दे रहा है। Is it clear? तो पहले हमने टर्न रेशियो निकाला, ये कितना आया 2400 डिवाइडेड बाय, ओके he is written wrong, it is yes 120, it comes out to be 20. Is it clear? We have already calculated it. Okay, now we know that primary voltage upon secondary voltage is turn ratio. Now secondary voltage is given how much, sorry, we have to find out secondary voltage. So secondary voltage is nothing but V primary divided by turn ratio. The secondary primary voltage is operating at 2300 volt. It is not operating at 2400 volt. कितने पे ऑपरेट कर रहा है 2300 वोल्ट पे। 2300 divided by 20. So the secondary will operate at 115 volt, but it will not operate at 120 volt. Is it clear or not? ये समझ में आया कि नहीं आया कि सेकेंडरी में कितना वोल्टेज होगा वो डिपेंड करेगा कि आपने प्राइमरी पे कितना लगाया है। आप हर समय रेटेड वोल्टेज नहीं लगाएंगे, आप उसे कम भी लगा सकते हैं या उसके बराबर भी लगा सकते हैं। ठीक है, तो वो टर्न रेशियो के अकॉर्डिंग सेकेंडरी पे भी वोल्टेज चेंज होगा। जैसे ये 120 पे ऑपरेट नहीं करके आप किस पे कर रहा है 115 वोल्ट पे। ये समझ में आया कि नहीं आया? अब सेकेंडरी करंट निकालना है तो हम पहले, हमें मालूम नहीं है कि प्राइमरी में करंट कितना है, तो हम पहले प्राइमरी का करंट निकाल लेते हैं। ठीक है, प्राइमरी या सेकेंडरी का किसी एक का करंट निकाल लेते हैं। सेकेंडरी का करंट कितना होगा केवी, हम केवी की मदद लेंगे। किसकी मदद लेंगे? केवी की मदद लेंगे। कैसे? हमें मालूम है जो किलो वोल्ट एम्पियर है वो क्या है, बेसिकली एपरेंट पावर या टोटल पावर, विच इज नथिंग बट वोल्टेज मल्टीप्लाई बाय करंट इनटू 1000। किलो का क्या हो गया 1000। अब हमें जैसे सेकेंडरी की तरफ निकालना है, ये कितना दिया हुआ है 25। let us check how much it is. I think so it is given, how much is given, let us check it. Oh sorry, okay, it is given 300 kV. So basically here something wrong is there. 300 kV, it is written 115 volt ampere, it is not 150. So it should be, I think so, 115 kVA. Okay, so it is not 300, it is 115 kVA. So let us check, correct it. So secondary current will be nothing but kVA multiplied by voltage. So it is 115 kVA, so it is 115 into 1000 divided by 150. So secondary current comes out to be 1000. Oh sorry, it is correct because sorry, it is written that it is operating at 115 kVA. It is not operating at 300 kVA, but it is operating at 115 kVA. So that is why we have chosen 115 kVA. Please make correction. It is 115 multiplied by 1000. kVA has been converted to volt ampere divided by secondary voltage. We will get the secondary current. So secondary current comes out to be 1000 ampere. Now, in ideal transformer, okay, the input power is equal to output power. There is secondary power is equal to primary power, or primary power is equal to secondary power. The same concept will be utilized here. We can, so you can find out the the same concept can be, because secondary current has also been asked, so you can find out the primary current also in a similar way. Now the third part is find load impedance seen on secondary side. Load impedance is nothing but secondary voltage divided by the secondary current. 115 divided by 1000, this comes out to be 0.155 ohm. Okay, next we'll find out its power factor, that is the impedance angle. Okay, now impedance angle is nothing but the we will find out the cos inverse of the so-called the power factor. Okay, that is 0.723 is the power factor angle, which is already being given. Okay, so we will find out cos inverse of this. So angle comes out to be minus 43.7 degree, which indicates that current is again lagging the voltage by an angle of 43.7 degree. Now it is asking find load impedance on seed on the primary side. So I have already Z load is nothing but Z input upon A square, that is the turn ratio square side. So that is the primary side is nothing but reflecting impedance from secondary to primary side multiplied by A square. So we will get the same thing here also, the same concept. Now the next topic will be of tomorrow's will be the non-ideal operation on no load condition. So far we have talked about the ideal operation. Okay, that is all losses are assumed to be zero, all leakage flux are assumed to be zero, permeability is said to be infinite. Okay, the magnetizing current is zero. So all these are the conditions of the ideal transformer, but practically there used to be there. Presence of losses also there, presence of leakage flux is there, presence of magnetizing current is also there. So now we will take into account all these things and again develop and again a model of the transformer, that how transformer will behave under the non-ideal condition. And we will take two conditions, one on the no load condition, another on the loaded condition. And the important point here will be the phasor diagram. So in the next class we will talk about the non-ideal operation of a transformer under no load conditions. So any doubt so far in this, please tell me, okay, in the chat box. Any doubt? एक्टिव पावर लॉसेस, एक्टिव पावर लॉसेस क्या होते हैं? एक्टिव पावर लॉसेस देखिए, एक्टिव पावर क्या होती है? एक्टिव पावर क्या होती है? VI cos phi. एक्टिव पावर क्या होती है? VI cos phi. Is it clear? I am writing here. This is active power. VI cos phi. Is it clear? और इसके एक साथ में एक और होती है, वो क्या होती है? रिएक्टिव पावर, that is VI sin phi for a single phase system. This is clear. Now this active power is always due to resistance, and this reactive power is due to either L or C. Clear? या तो L के कारण होती है या C के कारण होती है. कौन सी? रिएक्टिव पावर. रिएक्टिव पावर हमेशा किसके कारण होती है? रेजिस्टेंस. और रेजिस्टेंस किसका होगा? किसका होता है? कंडक्टर का. कंडक्टर इन अ ट्रांसफॉर्मर मींस वाइंडिंग. हमारे पास दो वाइंडिंग है, कौन सी है? प्राइमरी वाइंडिंग और सेकेंडरी वाइंडिंग. ठीक है, तो ये किसकी बनी हुई होती है? जो एक अच्छा ट्रांसफॉर्मर होगा कॉपर की बनी होती है, और कोई सस्ता ट्रांसफॉर्मर होगा उसमें एल्यूमिनियम की बनी होगी. ठीक है, तो इनका जो रेजिस्टेंस के कारण लॉसेस होता है वो कहलाता है कॉपर लॉस, और वही है हमारा एक्टिव पावर लॉस. रेजिस्टेंस के कारण जो लॉस हुआ दैट इज कॉल्ड एक्टिव पावर लॉस. Any doubt? Adhikari, is it clear? Any doubt so far? Please ask me.
Sir.
Yes? Anybody want to ask any question? There are few only students are joining. Out of the strength of more than 70, only 36 students are there, which is really not a good strength, in fact. And I have to take a strict action if the strength will remain like this. Any doubt so far?
No, sir.
Okay.
Sir.
Yes? No? Then that's all for today. Okay, we will meet in the next meeting. Thank you.
Thank you, sir.
Thank you.